So in the last lecture, we were solving a problem of rectangular footing. Okay, we were having the column size. Uh, just a moment. So the column size was, it is zero point 0.4 by 0.6 meter. This is the column, and our footing size it is 3.8 meter by 4.05 meter. Okay, we have completed the depth calculation from two-way shear consideration, and from two-way shear consideration we got the depth as 730 mm, that is 0.73 meter. Now we will calculate the depth by one-way shear consideration. Okay, so we have also started that one-way shear consideration, one-way shear, up to which point we have completed. Just I am giving recap to you. So one-way shear consideration we have started in the last lecture itself. Okay, and in that we have found out the area of strip A1. This A1 area which is greater, this area is 4.05 into, it is 1 point, this area which was greater area, 1.73 into something was there. Okay, 1.73 into, I think, 1.7 minus d. Okay, 1.73 into 1.7 minus d. This is the area of the strip. Okay, so this is having greater area. Okay, so now we will move further, and now we will calculate the depth from one-way shear consideration. Okay, so now we will move next, calculate the shear force. So shear force Vu is equal to, shear force Vu is equal to, so what was, how to calculate the shear force? It is very simple, stress into area, our basic formula. So stress is nothing but soil pressure, which we considered over here. Okay, so now what is the soil pressure? It is 204.67, multiplied by area. So area is 4.05 into, it is 1.7 minus d. So this is the equation for the shear force. Now you can simplify this a little bit further, so that what we will get, Vu is equal to, okay, you can multiply this quantity and then multiply inside the bracket. So it is 204.67 multiplied by 4.05. It works out to be 828.91. Okay, so into 1.7. So this quantity is 1409.15 minus. Now again it is 828.91 d. Okay, so this is our equation number 3. First two equations are in two-way shear consideration. Now this is one-way shear consideration. So after that we will see the shear resisted by concrete. So as we know that shear resisted by concrete is equal to tau CBD. This is the formula to calculate the shear resisted by concrete. So the first thing is we need to calculate the value of tau C. So already we have calculated the value of tau C. You know that the tau C is equal to how much? It is 0.25 under root FCK. So under root 20 into 0.25. that value comes out to be 1.118 Newton per mm square. Okay, so I will write over here once again so that you will understand. So you know that tau c is equal to how much? It is 0.25 under root fck. This is the value of tau c, which is equal to how much? It is 0.25 under root 20, which is again equal to 1.118 Newton per mm square. So if we convert it into kilonewton per meter square, then it will become multiplied by 10 raised to 3. So it is 1118 kilonewton per meter square. So this is the value of tau c. So we know the value of tau c, okay, and we know B and D, area of the strip. Okay, so it is width of the strip, that is 4.05 into D. So here I can write the formula. VUC, that is shear resisted by concrete, is equal to tau c 1118 stress into area. So in this case now area is 4.05 multiplied by D. Okay. I hope now it is clear to you how it is 4.05 multiplied by D. So now if I draw the strip once again, I will tell you this. So here I will draw the strip. So now suppose this is your strip. You can also draw these diagrams with me so that when you will do study you will understand how these values are, from where we got these values. Okay. So this is our strip, and now here it is the depth. Okay, so the drawing is not perfect, but it is, you can understand this. So now see which are the dimensions are there. I will give the dimensions. So this is our depth. Okay. Here from this point, this is your distance 4.05, and for this side this is your 1.73 minus D. So I will give right over here. This dimension is, we have already calculated, 1.7 minus D. This dimension. This is your depth, and this is 4.05 meter. Okay. So which area we consider for one-way shear? So if I show the area by hatching, then this area we should consider. Okay. This area we need to consider over here. So how much is this area? So if you see, this is 4.05 and this is your depth. This dimension is D. So it is 4.05 into D. That is why here the area is considered as 4.05 into D. Okay. So that is why here it is considered as 4.05 into D. So now we will move to the next part. So now if you do the calculation here registered by concrete, so it was 1.1118 into 4.05, so it is 4527.9 into D. Okay, so this will become your equation number 4. So now equate equation 3 and 4. So equating equation 3 and equation 4. So what was our equation 3? What was our equation 3? Can anybody tell me, because it was getting disconnected, so I don't have that slide with me right now. Can you tell me in the chat what was our equation 3? Anyone? What was the equation 3? Are you writing down something or not? What I am asking. What was our equation number 3? Okay. So it is 1409.15 minus 828.91 D. This is our equation number 3, which we will equate it to 4527.9 D. Now solve this equation so that we will get the value of D. So to solve this equation, D is equal to, how much it is? 4527.9 minus 828.91. So what is the value? It is 3698.99. Okay. So now we will divide it by, so it is 1409.15. It works out to be 0.380 meter, which is equal to 380 mm. Please check the calculation. Check the calculation. Okay. So this is the depth which we got from one-way shear consideration. This is the depth we got from one-way shear consideration. So here we can write, provide the maximum depth, provide provide the maximum depth, provide the maximum depth from one-way shear one-way shear and two-way shear criteria. So what is the maximum depth we got? Now the maximum depth is 0.73 meter, which is equal to 730 mm. Please check the previous calculations. Are we taking the value which we actually got, or it is something more? Please check the calculation. So now effective depth is 730 mm. Okay, so we will assume clear cover of 50 mm and bar diameter of 16 mm. So further I will write, assuming, what we are going to assume, assuming clear cover which is equal to 50 mm. For footing it is 50 mm, and bar diameter 16 mm. So we have assumed 16 mm dia bars. So we will calculate the overall depth now. So overall depth, capital D is equal to, how do we calculate capital D? So your effective depth plus clear cover plus half of bar diameter, So how much it is? Calculate now. It is 788 mm. 788 mm. So we will round this depth to 790 mm. Okay. We will round this depth to 790 mm. So now here we will calculate the effective depth again. So D is equal to, what is the effective depth now? So D is equal to 790 minus 50 minus 16 by 2, reverse calculation. So 790 minus 50 minus 16 by 2. So it is 732 mm. So now in this point, now just to focus on this, suppose now, uh, see, this is our footing. Just I will draw a box so that you will understand. In the effective depth, I'm talking about this effective depth. So now this is your footing, and above this the column is there. This is sectional elevation. Okay, and now see these bars. Suppose now direction I will mark over here. Okay, so suppose this direction is x direction and this direction is y direction. Okay, not upward. So I will see this is y direction, this direction is y direction. Okay, so I will write this is your y direction and this is x direction. So exactly where is the y direction? If I show it by some dotted line, see the length which is behind this, okay, here the footing will continue like this. Okay, behind. So this is your y direction. So in plan, if I show you, if I draw the plan of this, so if this is the plan, so in plan it will be clear to you. So which is x direction? So in plan now, if you see, this direction is x direction and this direction is y direction. Okay, I hope now it is clear to you. So as x direction is 3.08 meter and y direction is 4.05 meter. So what I am trying to tell you over here is, now see you have calculated this effective depth 732 mm. So how we have calculated the effective depth? We know this overall depth first. We have calculated this overall depth. Okay. So how much this overall depth? This is 790. This overall depth is 790, which we have calculated just now. Okay. So 732 means from top. Okay, you minus clear cover and bar diameter. So if I draw that, so here the bar will be somewhere here. This is the bar. This is the bar. And if we measure it from top up to the center of this, okay, so this dimension is nothing but it is a 732. So this is in x direction. What I want to say, this 732 depth is there. This is the effective depth in x direction. Now if you think about y direction, after providing some reinforcement in x direction, this is your reinforcement in x direction, this is the steel which we will provide in x direction, okay, at this depth. Okay, so above the steel of x direction there will be the steel of y direction. So above this, now if I draw, here will be the steel in y direction, these bars will show to us in this direction. Okay, same, if the same I draw in the plan. Okay, if the same thing if I draw in the plan, then it will be like this is your steel in x direction, these are your bars in x direction. Okay, and above that we will get the bars in y direction, these are your bars in y direction. Okay, these are your bars in y direction. And now if you see from this side, now if you see this from this side, okay, now if you see from this side, okay, this is your view, you are seeing from this side. then what you will get, this is the diagram which I have drawn on the top. If you seen from this side, this horizontal bar you will see, this is the horizontal bar which is in x direction, and these are the bars in y direction. You will see the diameter of those bars, diameter of those bars. So this is the elevation. So now this 732 depth, it is for steel in x direction. For steel in y direction now, from this point you need to go up to the center of this point. Okay. So this is your depth for the steel in y direction. Okay. So this is your depth. If I show you, this is your steel in y direction, and the depth will be, again, what is the depth? So total is 790. Total is 790. From that you have to minus clear cover. That is how much? 50 mm. Then you need to minus this bar in x direction. It is of 16 mm. And then again minus half of this bar diameter. Okay. So that is what I want to tell you over here. If you calculate this depth at the end, suppose while calculating the bending moment, then also it is okay. If you see closely the last numerical which we have solved, in that we have calculated the steel in x direction, steel in y direction. In that calculation, see the effective depth. So effective depth in x direction is different, effective depth in y direction is different. Okay, that is what I want to say over here to you, to clear the concept. Once your concept is clear, you can solve many problems. Okay, so this is your depth in x direction. Similarly, depth in y direction, it is again 790 minus 50 minus bar in x direction minus half of the bar in y direction. So assume that in x direction, in y direction, you are providing the same bar, 16 mm. So what is your effective depth in y direction? It is 716 mm. Okay, 716 mm. So now, after this calculation of the depth, what is our next step? Bending moment calculation. So the next thing is bending moment. Okay, so the next thing is bending moment. So how do we calculate now? For the bending moment, we know that we take the critical section at the face of the column. So I will write here, for bending moment, the critical section is is taken at the face of column. Okay, so now we will draw the diagram. So here, this inside one is your column. Our column is rectangular column. Outside I will draw the footing. So this is our footing. So if you give the dimension to this, then this dimension, it is 3.8 meter. This total dimension, it is 4.05 meter. So this is 3.8 meter and this is 4.05 meter. This side is zero point 0.4 meter for column. This side is 0.6 meter. 0.6. So now, to calculate the bending moment in x and y direction, we will take the sections accordingly. Okay. So first we will take our first section, and that too in y direction. So this is our first section along the face of the column. So this is our first section. Okay, along the face of the column. So this is our section YY. As it is vertical, so I am giving the name to this section is YY section. So now in this section, what we will do generally, we will calculate the UDL. Okay, so what we will do, this will become our span, this distance will become our span, and on this distance we will calculate the UDL. Okay, we will calculate the UDL which is coming on this distance, and we will take, suppose now this length is about y we are calculating, so let us assume that this length is Ly and this UDL is Wy. So we will calculate our bending moment along y direction. It will be Wy into Ly, that is W into L effective, uh, L effective. Okay, so it is WL square by, okay. So our main job is to calculate this Wy because Ly is already known to us. So how do we calculate the length now? So for that purpose, what we will do, so this total is 3.8, this is 0.4. So what was the remaining length? Now if I want to calculate this remaining length, this, what is this span, how much it is, that I want to know. So how to calculate that? It is 3.8 minus 0.4 divided by 2. So this is 1.7. This is 1.7 meter. Now UDL in y direction. How to calculate the UDL in y direction? So now if I consider this strip, if I consider this total strip, this strip, so I know that what is the stress intensity over here. The stress intensity we have already calculated, sigma, that is stress, it is 204.67, it is in kilonewton per meter square. So we know that we are having the stress in kilonewton per meter square, and if we multiply this by meter, then we will get the intensity or UDL in kilonewton per meter. Okay, because 1 meter square and meter will get cancelled, and we will get it in kilonewton per meter. Okay, now along which length we want UDL? Along 1.7 we want UDL. Okay, along 1.7 length. So per meter length we want this UDL. Okay, so now we will multiply it by which length? This 4.05. Okay, so here WY if I want to calculate, okay, then it is, that is stress intensity 204.67 and multiply by, what is this length, this length, because we want UDL along this length, so we will multiply by the opposite length. So opposite length is 4.05, so multiply this by 4.05, so you will get this UDL. So it is 204.67 multiplied by 4.05, so it works out to be 829, sorry, 828.91 kilonewton per meter. This is our WY, and LY is 1.7 meter. So your bending moment, ultimately your bending moment along section Y, okay, in Y direction, it is WL square by 2. So your W is 91 into L square, L is 1.7 square, okay, whole divided by 2. So if you solve this, it is 1197. Please check the calculation. 0.78 kilonewton meter. Okay. 28.97 into 1.7 square divided by 2. It is 1197 kilonewton meter. This is the bending moment in y direction. Now similarly we will calculate the bending moment in x direction. To calculate the bending moment in x direction, we will consider the section in that direction. Yeah. So I will draw the section over here. So this is the section along the face. So this is XX, section XX. So similarly now we will calculate WX first. So WX is equal to how much it is? Again stress, we know the soil pressure 204.67. Now in this case, if you see in this case now, so we will calculate the UDL along this length. Okay, so if I show you the UDL, this is the UDL like this, and this is the UDL, we called it as WX, and our span, this length, this is the length, and we call this as LX. So here WX is equal to, now we want UDL along this direction. So if you consider this total whole strip, this whole area, we want the load per unit this length, okay, LX. So we will multiply by other side is 3.8. So you should multiply over here by 3.8. So now it works out to be 204.67 multiplied by 3.08. So it is 630.38 kilonewton per meter. And what is your LX? LX is the length. Now LX, how to calculate the LX? LX is this much of the length. So how to calculate this? This total is 4.05 minus 0.6 by 2. Okay. So from center this is half and this is 0.3. So it is 4.05 minus 0.6 whole divided by 2. So it is 1.73. So your value of Lx is 1.73 meter. So take this value as 1.73 meter. And now calculate the bending moment along x direction. So bending moment along x direction, it is UDL, that is 630.38 into 1.73 square divided by 2. WX is 777.74, 204.67 multiplied by 3.8. Okay, correct, 777.67. Right. So this value is 777.746. Okay, so I will write once again here also, change this value 777.746. So now do the calculation. It is 777.746 into 1.73 square whole divided by 2. So it is 1163.85 kilonewton meter. So these are the bending moments in x and y direction respectively. So now you know the values of bending moments in x and y direction. So now provide steel along x direction and along y direction. Okay. So we will provide the steel along x direction as well as along y direction. So here what we will do, we will calculate steel by using our regular formula. So calculate the steel now. So before doing the calculation of the steel now, suppose if I rotate this, suppose now if I draw it like this, okay, if I rotate the figure, so suppose now this is 0.6, this is 0.4, this is our column, and now if we draw the footing, so this is our footing, Okay, it doesn't matter, no, just we are rotating. This is 4.05 meter, this is 3.08 meter. So while providing the steel, now I will draw the column over here. Okay. Now you have calculated the bending moment. You know what is the bending moment parallel to this along this 4.05 meter. Okay, so this is the 4.05 meter. So what we generally do now, if I give you here, this is 4.05 meter, and here it is 3.8 meter. So whatever may be the smallest dimension. Now this 4.05 meter is the larger dimension. So we will consider this 4.05 meter as our length, and this 3.8 meter is the smallest dimension. So we consider that 3.8 meter as our width. Okay. So here what we will do, whatever is the width of this, okay, we will take, we will plot same section over here. Suppose now I will draw this line. We'll take the same dimension, okay, and now this dimension is 3.8 meter. We will take same, okay, and this is called as central band. This is called as central band, and we will provide the steel in central band according to IS 456 2000, and this provision is given on page number 65. How to provide that, what to do that I will tell you while doing the steel calculation. But just you should understand what is the central band in the footing. So this central band concept is only for the rectangular footing. In the case of square footing, you don't need to calculate the steel for this central band. Okay. But in the case of rectangular footing, what we generally assume, whatever our larger dimension is there, that is our length of the footing, and whatever may be our smaller direction, that is width of the footing. Okay, and what we do, we plot this width of the footing along the length of the footing in such a way that from the center of the footing, if this is 3.8 meter, so from the center of footing we will go 1.9 meter this side, आपलं बरोबर की हाँ 1.9 meter on left hand side and 1.9 meter on the right hand side, so this total will become 3.8 meter. So we plot this width along the length, okay, and whatever may be the area we got, now this area is 3.8 meter by 3.8 meter, this area, okay, this is called as central band. This is called as central band. And now what portion is remaining outside? Now if you see how much is this length and how much is the length on this side. So now if you see that, then how much it is? It is 4.05 minus 3.8 divided by 2. So 0.13, almost 125. 0.125 meter, and this also 0.125 meter. Okay, this is called as end band. So we will provide the steel in central band, and there is a formula to provide the steel in central band. Okay. Now we have calculated the bending moment in x as well as in y direction. So instead of saying x and y, we will say that bending moment along 4.05 meter length and bending moment along 3.8 meter length. Okay. So see, I will write here bending moment along length of 4.05 meter, that is how much 4.05 meter means our bending moment in y direction. What was the value for that? What was the value? This bending moment in y direction. It is along the length of 4.05 meter. What was the value? 1197. Okay, 1197.78 kilonewton meter. Okay, and now the bending moment along width of 3.8 meter, that is your bending moment in x direction. How much it is? 1163.74 kilonewton meter. Okay, so these are the important words. I will highlight this. Okay, you pay attention over these here. 4.05 instead of highlighting it. Okay, and this. So bending moment along the length of 4.05 meter. This is our bending moment in y direction. Okay, so this is bending moment in y direction and this is bending moment in x direction. I hope now. Okay. So x direction means don't assume that your x is always horizontal. You can also see here now width, we have shifted width 3.08 meter as our width. Okay, so you can change the notation, it doesn't matter, the concept is most important. If you don't write this, हे तुम्ही लिहिलं जरी नसलं असतं, असं लिहिलं नाही तरी चालतंय, एक्स वाय काय लिहिलं नाही तरी चालतंय, but you should know this bending moment 1197 where I have found out along the length of 4.05 meter. That is most important thing. This 1163 bending moment, where do I find out this bending moment? It is along the width, that is 3.8 meter. That is the most important thing. The notation doesn't matter. Okay. So now steel calculation. So here I will give the heading steel calculation. So you know that while calculating the steel, now here we are considering the bending moment along length of 4.05 meter. Okay. So therefore our MU, that is bending moment, here it is 1197.78 kilonewton meter. Now use the formula. AST is equal to 0.5 FCK BT divided by Fy in bracket 1 minus under root 1 minus 4.6 mu upon FCKBD square. So put the values, you will get the answer and let me know the answer. So how much is the value of AST? 4699.07 mm square. Please check the values. So this is the value. Okay. Now calculate the number of bars. So divide this by 16 mm diameter bar. So it is 23.37. Okay, so the near about 24 bars are required for this. And if we take the 20 mm bar diameter, then okay, so instead of 60 mm, if you go for 20 mm bar diameter, then what will happen? 4699.07 divided by 20 square. Okay. So it will be 15 bars. 15 bars are required. Okay. So we will go for 20 diameter bars instead of 16 That difference can be tolerable. It doesn't matter much more. So here I will write taking 20 diameter bars for steel reinforcement. Steel reinforcement. Okay. So therefore AST. So this is our steel in longer direction. Okay. 4.05 is our longer direction. So this is our steel AST in longer direction. Okay. So AST in longer direction. As our 4.50 dimension is longer, it is 4699.07 mm square. So now calculate number of bars. Number of bars is equal to, it is how much, 4699.07 divided by pi by 4 into 20 square. So if we solve this, we will get the number of bars. So it is 4699.07 divided by 20 square. 14.95. It is 14.95, which is nearly equal to 15 numbers. So AST provided in longer direction. How much it is? 15 number of bars into area of each bar is, diameter of each bar is 20 mm. So calculate that AST provided. It works out to be 4712.38 mm square. This is the AST provided. Okay. Now calculate the spacing of these bars. Calculate the spacing of these bars. So the spacing of the bar, so spacing S is equal to, how do we calculate the spacing? Area of single bar divided by this provided AST multiplied by width. Now what is the width? Here you understand that we are not doing the per meter width analysis. Like, okay, so here the width is, what is the width? If you are calculating along longer direction, then it means that your length is 4.05 meter, and along that length you are calculating the steel, means parallel to the length, this length you are calculating the steel. So your another dimension becomes your width. So it is 3800. This is your width. So calculate the spacing now. It is 253. It is 253.33, which is nearly equal to 250 mm center to center. Okay. So here you can say provide. So here I can say along longer direction. Along longer direction. Longer direction means direction of 4.05 meter. Provide 15 bars of 20 diameter about 250 center to center. Okay, so this is for the steel along longer direction. This is for the steel along longer direction. Now we will move for the steel along shorter direction. So now along shorter direction. So along shorter direction. That is, what is the direction? It is 3.8 meter. Along 3.8 meter. So now how much it is? So the values are, for this you know that now your bending moment is something, what is there, 1163.74. Okay, and your depth is 716. So here your mu is 1163.74 kilonewton meter, and your depth, effective depth, it is 716. Okay, so now what we are going to do over here, calculating AST. What is the area of steel? So you know the formula, 0.5 FCKBD divided by Fy, in bracket 1 minus under root 1 minus 4.6 mu upon FCKBD square. So now if you solve this, you will get the value of AST. Solve it and let me know the value. So it works out to be 4659.28 mm square. Okay. So calculate the number of bars. Number of bars is equal to is 4659.28 divided by area of single bar. Assume that 20 mm diameter bars, so 20 divided by how much it is. So it is again 14.83 number of bars, which is nearly equal to 15 numbers. So 15 number of bars. Okay. So what is AST provided in shorter direction? So in shorter direction, AST provided is equal to again 15 into 5 by 4 into 20 square. So the answer is it is 4712.38 mm square. So this is the AST provided in shorter direction. Now we will move to the AST in central band. Now what is the central band? See what we have done up till now. This is our footing. Now only I am talking about the footing. So this dimension is 4.05 meter, and now this is 3.8 meter. So we will project this width, shorter dimension, along the longer dimension. Okay, so how we will project it? Now here, see, if I draw these lines, this part, so this is, I will give the dimension arrows so that you can understand it better. If you see this length, this is 4.05 meter, this is 3.8 meter, and now this 3.8 meter is projected along the length. So if you see this one, now this is your 3.8 meter, this area, and what is remaining now? So if you want to see what is the remaining, if we want to measure that dimension, then this dimension we need to calculate. It is 0.125. So this is 0.125 meter. This is also 0.125 meter. Okay. So this is, here we will calculate AST in central band. Okay, central band. This is called as central band. And now here at this point we want to calculate the ST. Up till now what we have calculated, we know that we need to provide along this direction. So parallel to this direction, whatever our steel is there, that is 15 number of bars of 20 mm diameter, 15 bars we are providing over here. Okay, and same way parallel to the shorter direction, again 15 bars will be there, which we are going to provide vertically along parallel to 3.8. But AST for this central band, now we will move to the IS code. So here in the IS code we can see what the provision is given. Open page number 65. So this is the IS code. So now if you read carefully, what does it says? Okay. Uh, so for square footing there is no problem. Okay. See here, square footing. The reinforcement extending in each direction shall be distributed uniformly across the full width of the footing. Okay, now whatever we are doing in square footing, it is fine. There is no problem. Okay, here it is, they have mentioned that. But when you talk about this rectangular footing, here, in two-way reinforced rectangular footing, the reinforcement in the longer direction shall be distributed uniformly across the full width of the footing. For the reinforcement in shorter direction, a central band, see here, for the a central band equal to the width, central band equal to the width of the footing shall be marked along the length of the footing. Okay, a central band equal to the width of the footing, whatever may be the width of the footing shall be marked along the length of the footing. So that width you should mark along the length, and the portion of reinforcement determined in accordance with the equation given below. Okay, so that central band, how to calculate that? So see here, this formula is given over here. The formula is given. Okay, so reinforcement in central bandwidth divided by total reinforcement in short direction is equal to 2 upon beta plus 1. And now they have further specified that what is this beta. So where the beta is the ratio of longer side to the shorter side of the footing. So beta is the ratio of longer side to the shorter side of the footing. So we will use the different notation for this. So here I will tell you reinforcement in central band. So we will use that this as this. For this we will use the notation AST central. Hmm? So, and the total reinforcement in shorter direction, this we have already calculated. Okay, so the AST in shorter direction we already know. AST short. Beta is the ratio of what they have said. Beta is the ratio of, now what is beta? Beta is the ratio of long side to the short side of the footing. So longer side is 4.05, short side is 3.8. So this is the value of beta. So this we will take now, 2 upon beta plus 1, this formula here. So, so now this formula we will apply. So here I will write, again I will draw the diagram. 3.8 meter, this also 3.8 meter, and this total is 4.05 meter. This total is 4.05 meter. Here it is 3.8 meter. This is 3.8 meter. So now this is our central band for which we are calculating the AST. So here I will write from IS 456-2000. Now you write the clause number. I will write page number 65. You yourself find that clause on page number 65. The AST in central band divided by AST in shorter direction. What was the value of AST in shorter direction? Can anybody tell me? 2 upon beta plus 1. So here AST in shorter direction. So shorter means along 3.8. What AST we have calculated. So AST central. Let me know the value fast. What was the value? 4712.38. Okay. So 4712.38 is equal to 2 divided by beta. So beta is the ratio of longer side to the shorter side. You can take it is the unitless quantity as it is the ratio. So mm मध्ये घ्या मीटर मध्ये घ्या काय फरक नाही पडत. So beta is equal to it is longer side 4.05 divided by shorter side 3.8 plus 1. So if you solve that you will get the AST in central band. And this you should do only for rectangular footing, not for the square footing. So it is 4.05 divided by 3.81. So it works out to be 4562.30 mm square. Okay, in the central band. So calculate the number of bars over there. So the number of bars is equal to it is 4562.30 divided by pi by 4 into 20 square. So here answer divided by 5 by 4 into 20 square. So 4562.30 into 20 square. So it is 14.52. Okay, so it is near about 14.52. So it is near about 15 numbers. Okay, 15 number of bars we need to provide over there. So lastly, if we draw the reinforcement details, okay, so I will draw the details now. So after the calculation of steel and all these things now, we will draw the reinforcement details along the elevation. So this is column, and I will draw the footing like this. So this is our footing. So we are seeing this along the length. So this I will give the dimension so that it is clear to you which sectional elevation we are seeing over here. So this is 4.05 meter. Okay, and this is your depth of the footing. This total depth it is 790 mm. So now the steel along this parallel to this, that bar we will lay down over here first. So this is the steel. Okay. These are the bars. Okay, so this is the bar. This is 20 diameter bar. About what was the spacing initially? Spacing of this bar is I think 250 parallel to 4.5 meter. What was the spacing? 250 Okay, and now steel in steel along shorter direction. So we will show over here the same steel. The central band again 15 number of bars will be there. Okay, so here the central band. These are again same reinforcement 20 bars. 10 number of bars are requirements again. How much is the spacing of this? How much is the spacing? 44050 divided by 10, 270. The spacing of this bar is 270, about 270 center to center. Okay, so these are the bars. This is the reinforcement. You can show the bars which are coming from the column also. If you want, you can show. These are the bars. These are called as trowel bars. These are called as trowel bars, which comes from the column to the footing. So these bars are like this. Okay. So this is the reinforcement details for the rectangular footing. Now we have taken one problem for rectangular footing and one problem for what we can say this square footing. Okay. So now unit number third and unit number four, that is retaining wall and water tank, we will take the last. Now we will start with the unit number 5, second section. We will start with the second section, prestressed concrete, and after that unit number 5, introduction to prestressed concrete concept, systems and methods of prestress. So what is the prestress member? So first I will read and then I will explain over here. A prestressed concrete member is a member of a concrete in which internal stresses are introduced in a planned manner so that the stresses resulting from the loads are counteracted to a desired degree. Okay, काही तुम्हाला समजलं नसेल, so I will explain that. What is the prestressed concrete member? So now suppose this is a beam. Okay, and now the reinforcement is provided here in this beam. So what they generally do, suppose this is the bar. Oh, sorry. Suppose this is the bar. Reinforcement is provided over here. Okay. So what this is, internal stresses are introduced in a planned manner so that the stresses resulting from the loads are counteracted to desired degree. So how which stresses are developed due to the loads? Now suppose the load is acting over here like this. Load is acting. Okay. Suppose this is UDL. UDL or point load. What type of stresses developed here in this on this beam? So two types of stresses are developed. First is first is the direct stress. Okay, direct stress. And second thing it is bending stress. Okay, bending stress. these two major stresses are get developed over here. Okay, so to resist this direct and bending stress, what we do, we develop some internal stresses inside this concrete member. So what we will do now, this is our steel bar. This is our steel bar. So externally, we it is like this now. I will extend this bar. Okay, and now on this bar externally we will apply some stresses. Okay, externally the stress is applied on this bar. Okay, and this applied stress is called as prestress. This applied stress is called as prestress, and due to this applied prestress, the stresses are generated in this bar. The stresses are getting induced in this bar, and those stresses are opposite in nature to this bending stresses. Okay, the stresses which are generated in this bar, these are an opposite nature to this बेंडिंग स्ट्रेसेस. म्हणजे काय केलेलं असतंय तर हे बीम ज्या वेळेला कास्ट करत असताय तर ते बीम कास्ट करताना जेव्हा तुम्ही स्टील रिन्फोर्समेंट ह्याच्यामध्ये टाकता तर त्यावेळेला या बीम्सला इथं होल केलेले असते, त्या होल मधनं हे स्टील बाहेर काढलं जातं. ओके, अँड ज्या वेळेला तुमच्या आता ते कॉन्क्रिटिंग करणार आहे त्याच्यात थोडा वेळ आधी ह्या स्टील बार्सला इथं जॅक फिटिंग अरेंजमेंट केलेली असते, स्क्रू बे अटॅच केलेले असतात. ओके, आणि त्या जॅक हॅमरनी ह्याला स्ट्रेस दिला जातो म्हणजे स्ट्रेस ह्याच्यामध्ये डेव्हलप केला जातो या स्टील मध्ये. ओके, द स्ट्रेस मे बी आयदर टेन्साइल और कॉम्प्रेसिव्ह, मोस्ट ऑफ द टाइम्स टेन्साइल स्ट्रेसेस. सो त्याच्याने काय होतंय की ड्यू टू विच द स्ट्रेसेस आर गेटिंग डेव्हलप्ड इन दिस स्टील. नाउ आफ्टर pouring the concrete, these bars are cut down from here. हे बार्स इथून कट केले जातात. And now already the stresses are induced in this steel. So this type of member is called as the prestressed member. So pre means agodarach. So stress is given to the steel. And what was the result of this? Now if you given the prestress to the steel, that prestress is transferred to the concrete. That prestress is transferred to the concrete, and your steel and concrete both strength increases due to this external stress provided to the steel. And that is why if the strength of the concrete and steel is increased, this type of members are the prestressed members, and these members are usually used in big construction, that is big bridges, big girders. Those are prestressed concrete members. Okay, so now moving further, so again once again I will read. A prestressed concrete member is a member of a concrete in which the internal stresses are introduced in a planned manner. So we decide that which type of internal stresses we want to induce in that steel bar. Generally tensile stresses are induced so that the stresses resulting from the loads are counteracted to desired degree. So why we do this? So because the load which is coming on the structure due to the dead load and live load, some stresses are getting developed, direct stresses are there, bending stresses are there. To resist those stresses, uh, we do this. Okay, so now the next thing is some introductory part about that is given over here. Okay, so the first thing, the concrete has high concrete has high compressive strength as compared to its low tensile strength. The concrete has high compressive strength. You know that concrete is capable of taking the compression, but its tensile strength is very low. So it is not difficult to make a concrete which can have strength over 40 Newton per mm square on 150 cubes, 150 mm cubes after 20 days of curing. Okay. what it generally says that we can prepare a concrete M40 grade also, for the M40 grade also. Shiv, roll number one. Okay. So it is not difficult to make a concrete which can have a strength over 40 Newton per mm square. So we can make a concrete up to M40 grade, M50 grade, M60 grade. Okay, it is not difficult for us to increase the strength of the concrete, compressive strength of the concrete. But it is very difficult to obtain the tensile strength of the concrete greater than 2.5 Newton per mm square. See the gap. Okay, so it is not difficult to us to achieve the strength of the concrete up to 40 Newton per mm square, but it is very difficult for us to achieve the concrete tensile strength more than 2.5 Newton per mm square. See the difference in between the figures 2.5 and 40. Okay, so this is why concrete is reinforced with steel bars in such a directions where the tensile resistance has to be offered. So that is why the steel is used with the concrete and any member. Okay, so now the next point is the reinforced concrete members, due to the low tensile resistance of concrete, a large quantity of steel is provided. Okay, so concrete members मध्ये जनरली काय होतंय की आपण स्टील प्रोव्हाइड करतो ना. Why we provide steel? Because the low tensile resistance of the concrete. So that the entire tensile resistance is offered by the steel reinforcement. No special means are provided to prevent the concrete offering the tensile stresses. Okay. So you know that in a concrete member, total the tensile stress is resisted by the steel only. Okay. And concrete resists only the compressive stresses. Next point is in Prestress. Don't write down the notes these points. I will send this soft copy to everybody. Okay, on group I will give this soft copy to everyone. So there is no need to write it down. Hmm. Uh, so in Prestress concrete member, all above weakness and defects are made up. So whatever the points which we have talked about right from the top, that is the concrete is having higher strength 40 Newton per mm square, but its tensile strength is very low 2.5 Newton per mm square. That is why we mix concrete and steel together in a member. Okay, and where the tensile stresses are likely to be having a greater magnitude, there we provide the steel, and the concrete doesn't resist any tensile stresses. All it is taken care by the steel. So in prestressed concrete, so in normal you know that concrete only takes care about the compression and not about the tension. So in the prestressed concrete member, all above weaknesses and defects are made up. Okay, so all these what we can say weaknesses are there are come over. So in Prestressed concrete member, essentially a concrete member only, and the steel reinforcements are considered as a necessary device to supply the prestress to the concrete. Okay, so now the when we want to give the prestress to the concrete, okay, to increase its strength, it is not directly given to the concrete. What we generally do, we first apply the prestressing force to the steel, that is the tendon or bar or reinforcement which is provided over there. Okay, so we will apply the prestress on steel, and then steel will transfer that prestress to the concrete through bond action. Okay, to get the maximum advantage of prestressed concrete members, it is necessary to use high strength concrete and also high tensile steel. Okay, so in prestress we always use high strength concrete and high strength steel. Okay. So the concrete used for prestress work should have a cube strength of 35 Newton per mm square for post-tension system and 45 Newton per mm square for pre-tension system. So what is this post tension system and what is the pre tension system, that we will see later on. Okay, just now you see a concrete which we are using for prestressed work should have a minimum cube strength of 35 Newton per mm square for post tensioning and 45 Newton per mm square for pre tensioning. Okay, these are the minimum cube strength. So M35 grade concrete minimum for post tension and M45 grade concrete minimum for pre tension system of the prestressing. So this is the classification of prestressed concrete. Okay, so classification of prestressed concrete members. So first, externally and internally prestressed members. This is the first thing, first classification. Then second, based on linear or circular prestressing, that is the type of prestressing. And third is the pre-tensioning and post-tensioning. So these are the three basic points along which we will classify the prestressed concrete members. So in short, we will see this. First, externally and internally prestressed members. So what is externally and internally prestressed members? A member can be prestressed by external reactions offered by rigid abutments is called as external prestressing. Now you can see this diagram. This is your prestressed member. This is the jack assembly which is provided over here, and this is the abutment. Okay, the abutment. So the prestressed force is provided to the member externally. So directly prestressed force is applied over here on this member. Okay, and this prestress is transferred to the member with the help of this jack and this abutment, this system. So this is the externally we are applying the prestressing force. So this is called as prestress member. So this you can see over here. This is the external prestressing. So externally stress is applied, prestress is applied on this prestressed member with the help of jack assembly. So this is called as external prestressing. Okay. So similarly, internal prestressing, in external prestressing, instead of providing the tendons, instead of in the external prestressing, instead of providing the tendons from which prestress can be applied, the necessary prestressing force can be applied by compressing the member by jack against the abutment as shown in above figure. So directly we apply the prestressing force on the member. This is called as external prestressing. And in internal prestressing, we are not directly applied the prestressing force. We applied the prestressing force on the steel. A member can be prestressed by tensioning the tendons. Tendons means bar or steel. Tensioning the tendons is called as internal prestressing. Okay. So these are the two basic types of external prestressing and internal prestressing. So today we will stop over here, and in the next lecture we will finish this unit, unit number 5. This is purely theoretical unit. Okay. So I will just tell you where there is a important point or important logic is there. I will explain you with the diagram here only. Okay. So in the tomorrow's lecture we will see what is pre-tensioning and what is post-tensioning. This is the important thing. This is the only important point. Okay, in this unit. These two are the important points. Okay. So basically in short I will tell you what is prestressing. नॉर्मली काय असतंय आपलं स्टील आणि कॉन्क्रीट घेतल्यावरती आपली एखादी बीम तयार होती. दॅट इज द नॉर्मल मेंबर. प्रिस्ट्रेसिंग मध्ये काय असतं माहिती का की तुम्ही जेव्हा ती बीम तयार करत असता त्यावेळेला काय असते, तुम्ही एखादी बीम घेतली तर त्याच्यामध्ये स्टील प्लेस करता. ओके, स्टील प्लेस केल्यावरती त्याच्यावरती आपण कॉन्क्रीट पोर करतो. मग याच्यात काय केलं जातं, ज्या वेळेला स्टील प्लेस केलेलं असतं की नाही तर त्या स्टीललाच एक्सटर्नली प्रेशर दिलं जातं. ओके, ते प्रेशर कसं दिलं जातं, काय दिलं जातं, दॅट इज डिफरंट पार्ट. दॅट इज बाय युजिंग जॅक असेंबली. ते तुम्हाला बघावं लागेल कसं असते ते इक्विपमेंट. ओके, तर त्याच्याने ते त्याच्यावरती काय केलं जातं, बाय युजिंग द जॅक असेंबली प्रेशर दिलं जातं. कुणावरती? स्टीलवरती. आणि त्या प्रेशरमुळे किंवा त्या लोडमुळे काय होतं की स्टीलमध्ये स्ट्रेस डेव्हलप होतो. ओके, मग स्टील मध्ये जर स्ट्रेस डेव्हलप झाला, इंटरनली स्ट्रेस डेव्हलप झाला, तर काय करतो आपण नंतर? कॉन्क्रीट आधी तरी पुअर केलेलं असतं किंवा नंतर तरी कॉन्क्रीट आपण पुअर करतो. जर कॉन्क्रीट आधी पुअर केलं तर त्याला म्हणायचं प्री टेन्शनिंग, आणि कॉन्क्रीट जर नंतर पुअर केलं त्याच्यावर तर त्याला म्हणायचं पोस्ट टेन्शनिंग. एवढं सिंपल आहे. आणि मग त्याच्यावरती कॉन्क्रीट जेव्हा तुम्ही पुअर करता तर ऑलरेडी त्या स्टीलला तुम्ही स्ट्रेस दिलेला आहे, तर तो जो दिलेला स्ट्रेस आहे तो स्टील कडून कुणाला ट्रान्सफर होतो? कॉन्क्रीटला, कारण कॉन्क्रीट आणि स्टील एकमेकाच्या कॉन्टॅक्ट मध्ये आले. आणि ह्याच्यामुळे काय होतंय, तर कॉन्क्रीटची सुद्धा स्ट्रेंथ वाढते आणि स्टीलची सुद्धा स्ट्रेंथ वाढते, आणि ह्याला म्हणायचं प्रिस्ट्रेस मेंबर. दॅट इज द ओनली कॉन्सेप्ट ऑफ प्रिस्ट्रेस. I hope now these points are clear to you. So in the tomorrow's lecture, we will continue the things. Okay. So to